So in terms of things that we've learnt during the EdenDTC project about the spatial patterns on the landscape, there's three key points I want to talk about today. The first is that the sources of the diffuse pollution risk within a landscape are not static, they're changing over time. Second, how we set about identifying these key critical source areas in the landscape determines on the results that we get, so no one method is providing an overview of the whole of the problem. And third is that the key source areas for different parts of water quality or ecological health vary across the landscape. So the first of these was really looking at the field scale and to look at how the potential for mobilisation of sediment changes both within fields and over the year. We looked at a set of three different fields within the moorland catchment, and the method we used was to build fine-scale geographical data using drone mapping, whereby you can fly across the catchment, survey it out, build a 3D model of the catchment like you can see here, and that then can be used to generate both a fine-scale DEM and an orthophoto. So the DEM you're looking at here has a data point, a measurement every 3 centimetres across that field, and the orthophoto has a colour value every 1.5 centimetres. Now, we mapped this out over the course of the year over multiple flights, over multiple surveys, and just visually from here you can see the grass establishing where it was reseeded in June and the re-establishment over July and August. If you look at the detail on the bottom set of images, you can see that we've got detail down to what's happening down to maybe within individual tyre tracks across the field. But to get this from a set of pictures to a set of values, we use an algorithm called VARI, which basically is an index of how green the land cover is. And the greener it is, the more vegetation there is, and the more vegetation, the more protection that soil surface has from the soil being mobilised from rainfall. And you can see here how the patterns vary across the field and how that changes over time. You can see how our peak mobilisation risk came out in June this year when the field was reseeded, and that dropped very rapidly into July due to the grass establishment. Now, as I mentioned, this approach also drops out detailed topographic data, and we can use that information to calculate indices of connectivity across the field. So here, the areas that are in blue in this image here have high connectivity, the areas in red have low connectivity, and we can combine that with those mobilisation risks to work out the hotspots across the catchment in terms of where the sediment is likely to be originating from for this particular field, and hence where we may want to change or be more careful in our management. So the first key take-home message I want to leave you with is that we need to reflect the dynamic nature of the landscape in our analysis and not rely on static published land cover maps such as the CH land cover map, for example. The next bit of work I want to talk to you about steps up a scale and was looking at the 2 kilometre squared subcatchment scale. And what we set about doing was saying, well, actually, where are the critical source areas for diffuse pollution across this 2 kilometre squared subcatchment? So this is for the moorland mitigation catchment. And the original idea was to take a weight of evidence approach and to combine what we can calculate using published data sets with desktop SCIMAP, combine that with the fine scale mapping from the drone mapping, and again feeding that through the SCIMAP algorithms, and combine that with an on-the-ground walkover survey across the catchment. So the SCIMAP-based approach is something I've worked on for many years, and the idea is to combine a detailed representation of the connectivity and the mobilisation risk to put them together to work out where the sediment is on material is most likely to be coming from within the catchment. So the desktop GIS data set that fed into this has the NextMap 5 metre DEM, the CH land cover map 2007, that was converted into a per field risk, and of the topography we can calculate the connectivity and the amount of energy available to mobilise material. And We did the same with the fine scale DEM, so that's the ortho photo there, the detailed DEM. Use the same Vari algorithm to calculate the mobilisation potential. And you can see here within the catchment, the fields which were bare at the time of the survey, the more arable fields, they're coming out of the higher risk as opposed to the more established grasslands in other parts of the area. And again, we calculated out the mobilisation and connectivity risk. Now, if we look at the comparison between the desktop 5 metre data and the fine scale connectivity mapping, which was run at 40 centimetres, you can see there's a significant step up in the amount of detail in the fine scale data, and it's particularly good at pulling out fine scale linear features such as field boundaries and tracks within the landscape. And it's also very good at representing the current land covers and current management of the fields. So you can see the impact of the ploughing in this field down here, for example, on the connectivity. But there's limits to how far you can map out with this approach. The sensible limit is probably about 10 kilometres squared, but with the new EA LiDAR datasets coming in over the course of the next year, then we'll be able to do this fine scale mapping for many more areas and a lot more catchments across the country. The third approach we did was a traditional walkover survey, working with a bespoke diffuse pollution mapping application on a smartphone, and we looked for locations across the catchment for both accelerating and decelerating features of diffuse pollution. And after we did this, it was 3-person days we spent walking around the catchment to collect this data set. I undertook a viewshed analysis to look at how much of the catchment we'd seen during those 3 days. And actually we managed to only see 63% of the overall catchment. Now, as I said, the idea behind this was to build a weight of evidence approach, and where each of these 3 methods agree on an area, that gives it a very strong weighting, strong confidence that we should act there. What we found, however, is we were almost perfect disagreement across the 3 different methods. So on this map here, the red squares, the red crosses, are where the Walkover survey identified accelerating features. The purple areas are desktop SCIMAP and the blue areas are drone SCIMAP. And as you can see, there's a lot of clustering around the walkover surveys, around features, particularly where there's a lot of animal traffic around the farms. And the fine scale mapping was able to pull out contemporary land use and smaller scale features, so that tracks come out as key features in the fine scale, which just aren't in the desktop data set. So the key messages here really is that one method doesn't provide you a full overview of the system and where the critical source areas are. And we need to take a multi-methods approach. And what I'd recommend is using desktop SCIMAP at the scale of the full catchment, at the full River Eden in our context here, to identify subcatchments which are of highest risk. Second, to then use a fine scale SCIMAP driven by the LiDAR data or drone mapping to get that detail within that small area, and combine that with the walkover surveys at that point to get to the key critical source areas within those catchments. The third piece of work I want to talk about is then stepping up to go, well, actually, how do we do this assessment at the catchment scale? I just said doing desktop SCIMAP at the catchment scale is a good idea. So what we found was that by looking at multiple different endpoints in terms of stream quality and ecological health, the source areas are different. Now, the reasons for this is as we move up from 10 to 2,300 kilometres squared, then what you'll see here is that there's a greater variation in elevation, in soils and land cover and rainfall across the catchment, and we need to capture that variability. So we undertook a survey across the whole catchment, and that looked at 34 sites across the Eden. They were selected based on the desktop SCIMAP risk weightings to capture across from low risk to high risk across the catchment, so we knew we were going to get that variability. And we analysed that for physical properties, so NPK, but also looked at the diatoms and the trophic diatom index as an index of the ecological health, and the chlorophyll A measured in situ. This then was fed into the more advanced version of SCIMAP, which is called SCIMAP Fitted. And here, what you're then trying to do is use the SCIMAP approach to reproduce the observed pattern of your determinants in the field. So it's trying to reproduce the pattern that we found of the physical properties and the chemical properties. And what we found out at the end was that actually the source areas for different aspects of ecological health and physical properties of the river system come from different parts of the landscape. So that in these maps here, the areas highlighted in red are the highest risk areas for that determinant, and that's where you'd go and act to improve things. But if you kind of compare and contrast between the areas highlighted in red for chlorophyll A versus the trophic diatom index on the right-hand side, you can see significant contrast, say, between the EMOT system, where we are now. The Pennine Becks are coming out very different between these two, and the earthing up in the north is also significantly different. So, the key take-home message here is that we shouldn't think that by fixing one aspect of the ecology of the river that everything else will follow. If we optimise things for chlorophyll A within streams, the diatoms won't necessarily follow the same results. So we need to be mindful of the potential conflict that we'll have between the goals of the catchment management in terms of improving ecological status of the river system against the success criteria that we may choose. So we may be successful in our criteria but fail in our goal. So the three main kind of summary points from this are that we need to undertake and look at a dynamic view of the landscape rather than static. And we've got the data sets, tools and techniques are now able to do that, but we need to build these into the operational tools and the management tools to get better outcomes. And third, we need to be mindful in how we place our mitigation features, both in terms of the method we use to calculate our critical source areas, but also then in terms of the endpoint and what we're using as our success criteria.